This unit is going to cover a whole lot. This really brings us into the 20th century modern physics. We're going to start with blackbody radiation, talk about quantized energy, and then the photoelectric effect. So, at the turn of the century, our understanding of the physical world was changing rapidly. The electron was discovered. There was evidence that the atom, which had been considered to be the tiniest particle of matter, actually had an internal structure. Cathode rays were found out to be particles. In fact, they were electrons. And the distinction of ray-like properties, in other words, light, and solid matter, such as particles, started to blur. Next, the very nature of light was to be challenged. All objects emit electromagnetic radiation. This radiation depends on their temperature, and as such is called thermal radiation. We're going to define what a black body is. A black body absorbs all electromagnetic radiation, such as light, that falls on it. No light is reflected or transmitted, so the object appears totally black when it is cold, hence the name black body. However, an interesting effect occurs when you heat these black bodies. They will emit a temperature-dependent spectrum, and it is called blackbody radiation. At normal temperatures, for example, room temperature, 30 degrees Celsius, we're not aware of this radiation. But as objects get hotter, we can feel the radiation, the infrared radiation or heat. So we have a couple examples over here. Here's a light, and you can see as it warms up, that's what's happening here. It's been turned on, it's warming up, and you can see it's glowing red. Okay? Now, at still hotter temperatures, this same object is going to glow white. Okay, white hot, such as the filament in this light bulb. So it started out red, keeps heating up, and we get it to a white color. The previous slide showed how an object changed color as it got warmer. Many people would be happy with that. However, Wilhelm Wien did many experiments, observed what happened. He actually came up with an equation. Again, this was not derived from any theory or thinking about it. He measured. So he found out that the color of light, which is lambda, the wavelength of light will tell you its color, times the temperature, where the temperature is given in Kelvin. When you multiply these two numbers together, you get the maximum, lambda maximum, times the temperature is equal to 0.28978 times 10 to the negative 2 meters Kelvin. That's what this unit is here. It's meters Kelvin. This is called Wien's displacement law, and basically it shows that the higher the temperature, the shorter the wavelength of the peak color of the light. Right? We have a constant over here, so as temperature goes up, in order to keep this side constant, the wavelength has to go down. So this shows that the object will change color from red to orange to blue and then finally to white. And basically what white is, all wavelengths are present in high intensity in the visible spectrum. So it's not infrared, it's not ultraviolet, it's stuff that we can see.